So I'm talking today a little bit about open optical networks, reality and ambition. So in particular, I'm talking about what is our ambition in TIP with open optical networks with the PSE team. Let's start a little bit from where we left. So the reality for not so long ago was really that we were all dealing with the same physics, but there was not really a way to interoperate, not between transponders, not plugging transponders into line systems. It was even a question, which parameters do you need to characterize in order to figure out that the line system works for you or for a specific transponder. So it's really like the picture here where we had a lot of organizations or a lot of companies working on transponders like the plugs, and a lot of other companies, they're working on the sockets. And if you happen to use the same vendor, or here this is the same plug, it worked. And if you had a different vendor, it didn't. Well, you could buy an adapter like the Apple one, which is a little bit of expensive, and obviously it was always a kind of a hassle to get things to work and to figure out which adapter you need for what. Similarly for optics, there was let's say different shaping, different parameters that has been used in order to guide the optical network for optimum performance, and there was no agreement in the industry about any of those. Now, fortunately, that changed, and it changed in 2013, or started to change in 2013. I was kind of digging it up to figure out when was really the birth of the idea of real open optical networks. And the earliest thing I could find in IT was 2013, when operators were really asking to standardize open forward error correction. There was a lot of work being done there. So you see it ended up in 2020 with G709. So it was 7 years in the making. While on parallel, OIF was working on interoperability on 400 gig. They started in 17 and ended, well, they only needed 3 years. But I also have to say, to the credit of ITU, there was a lot of work that ITU already did that could be used, that was carried over into OIF in order to speed it up. However, if you kind of ask yourself, okay, when was the birth of real available open optical networks? I would put the birth date at 2020. Then, for this talk, I was also thinking about what is reality and ambition. So we know in 2020, everything was available, at least on paper. But what is the industry picking up? And I found some very interesting figures from heavy reading. Let's start here on the left. So in 2020, there were some of the respondents saying, hey, we already have open optical networks implemented. Well, that sounds a little bit strange because, it just came out of the oven, so how can it be implemented? And the reason is that people had a completely divergent view of how open is open, what does open optical network really mean. In 2020, open optical network is basically alien wavelength support on single vendor optical networks. But what this figure also shows that there is a massive interest in open optical networking. If you go to 2020, basically, you can say, hey, about 60-65% of the operators that were interested in open optical networking, they should be in a position right now to have it already implemented in their network. Then we see it here on the right. So on the right is the interesting question of how you want to use this open optical network. So what is the link that you can be? Unamplified link, an amplified link, multi-span, ring mesh, all those topologies. And if you just look at it from a far away, you can say, well, it's kind of everything. So basically, what it means to me, and that's my personal interpretation, is the respondents at that point in time in 2021 didn't really know what to use open optical network for, right? So if you think about 400G CR, that's typically defined for unamplified and amplified single span. So you would naturally expect here these to be high, but using a CR for a multi-span point-to-point with intermediate amplifiers and ring mesh is a little bit of a stretch. However, there was the hope of using the interoperability that is now coming up for 400G CR on those networks as well. And that kind of opened up another application, which is the optical planning. So what we do in TIP, in the PSE group, is we came up with a vendor-agnostic open source optical planning capability. And that is impairment-aware planning. So we basically can simulate a network. So this is just one example. And you can try out, say, I want to use OpenCR Plus and go from Stuttgart location to Hamburg. So what is my margin? What I'm going to end up? Is it going to work? And that is exactly, if you look back, what I showed before, this is addressing that issue. You now have an open optical network, you now have open transponders. How can you make them work for your own network? So the combination of openness plus this planning capability really gives an operator an insight to say, where are the candidates, where can I deploy it? Where can I put my transponders from vendor A with a certain performance and still make the distance that I have in my network? Now, I have to say that this is planning. So let me detail it a little bit. So when you plan an optical network, you typically plan for a capacity of, say, 80 wavelengths per link, right? So you calculate what will be the performance of the worst channel once you put 80 wavelengths on each link. Now, that obviously leaves a lot of performance on the table because normally those networks are operated at, say, 20, 30, 40 wavelengths per link. So in daily operation, you have much more capacity, much more signal-to-noise ratio left that you could use for something else than what a planning tool would give you. And that is exactly what we're now addressing in our next adventure. So what is the future? What is our ambition? We want to have the self-aware optical network. What does it mean, self-aware? Most people believe self-aware means, if you, for example, if you take a hammer and you hurt your finger, you know you're hurt. But this has nothing to do with self-aware. Self-aware means that you see that somebody takes a hammer and it's going to hit your finger, so you're able to predict what's going to happen. And this is what we are going to do with a self-aware network. So, a few examples of what can be done with that. Number one, active quality of transmission assessment against plan. Remember, we plan the network, we know how the network should perform if all the wavelengths are full. But now you have a network, you started somewhere, you have maybe 10 wavelengths instead of 80. And the question is, am I still, with my current network, am I still in plan? So if I would add another 70 wavelengths on that link, would it still work, yes or no? So what we need to know is to predict, based on what there is right now, are we able to reach the 80 wavelengths? Yes or no? The second is the quality of transmission trending and impact prediction. So optical networks, they have a life. You know, you cut the link, you repair it, you need to change connectors, you need to clean them up. So over time, there is some degradation here and there. And the question is, where does it trend? So for example, assume you have your network, you have your 10 wavelengths, they're running, they're happy, everything is nice. And the optical impairments get worse. As long as you still have the 10 wavelengths, nothing is going to happen because you're far away from a limit. But now if you say, hey, I want to go to 40 wavelengths over there, how am I impacted? Is the trend that I'm currently seeing in my network, is that allowing me to go beyond what I have right now? Or you come up tomorrow, say, hey, I want to have an 800 gig in that link. Is that a safe choice? Or is that link kind of trending towards towards impairment that will really impact my 800 gig link? Another one is, and that's very important also for CapEx reason, narrowing the margins based on the allowable out-of-service probability. Now, when I talk about out-of-service probability, I'm talking about the wavelengths. So today, basically, what you do is when you come up with a wavelength with the implementation, you have an end-of-life margin, the network has an end-of-life margin, it has a system margin, they all add up. And there's a good reason for it, because you never really know what the margins in your network are right now. You can measure something, but you cannot really measure everything. So if you have a simulation tool that is able to take into account what the impairments of the actual network are and able to predict, you basically are able to narrow down the margins, the system margins that you need to set aside for your optical network. So, and by doing so, obviously, you can save a lot of capex, because you can use higher modulation schemes and really run the network a little bit hotter than it is today. So, with that kind of additional capability, we want to push open networking one notch further, and we're actually already working in the PSE team to add on those functionality together with our partners. And I would also invite everybody who is interested to come to work with us. It's an open source. You can participate like in every open source project. And yeah, we'd love to work with everybody who has really an interest in pushing openness forward in optical networks. Thank you very much.
Is this on? Okay. Yeah, thank you very much. In the interest of time, because we are running about 5 minutes behind, any questions for the speaker?
Hello, thank you for the talk. I'm Yvan Pointerier from Huawei. So I'm all for adaptive margins on low margin. However, the feedback we keep getting is that when you do a design, you have to carry the traffic, and that's about it. What do you do with the extra margin you have if it's not planned at the design time already? So that's really the question I would like to ask.
Yeah. So the question is, what extra margin are we talking about if it is not included in the design study already? The point here is, in a design study, you typically assume a wavelength occupation of your network of a certain thing, say 80 wavelengths on a specific link. However, as you ramp up the configuration, there's almost always enough budget to go to 40 wavelengths, for example. And you really don't realize that you end up in a regime we are not going to reach the 80 anymore. So some of the part that can be narrowed down is end of life. And I'm talking about end of life of the optical network, because that is also another thing. If you go today in an optical network that you're operating since 10 years and say, hey, the end of life margin that has been budgeted for that optical network was something, how far away are you now from what has been budgeted 10 years ago? And obviously there's a lot of things ongoing, so you have new amplifiers, you have new machines, maybe you repair fiber. So this kind of question of what was the target at the time and where do I stand now that is something that is very hard to answer, and that is what we are really looking into. Say, okay, where do we stay now in comparison to what has been planned right before?
Okay, thank you very much. I'd like to thank the speaker. It's really good.
Thank you.
Thank you very much.